Okay, so we're back talking about 2.7, and where we left off was talking about even and odd functions, and you were going to do these practice problems. So that's where we're going to start off answering these. The first one, you may just know what they look like and be able to visually tell about the symmetry. You know, that really helps me. Or you can use your graphing calculator or your app to do that as well. So if it's x squared, I can kind of see it folds along the y-axis. So that's y-axis symmetry. Oh, and also I'm supposed to see if that's even or odd, sorry. So it's y-axis symmetry, which means it's an even function. And that may just seem just a little bit obvious where it's x squared to you, maybe. The next one is x cubed. X cubed swirls around like this. And that is an odd function. Again, it may seem a little obvious on those. If there's just even exponents, well, it's an even function. If they're just odd exponents, it's an odd function. So kind of like what you'd expect. But it's not always just that clear, because sometimes there's extra stuff on it, so we have to think a little deeper. So again, you might just graph that. We know how to graph a line. That would be starting at 1 and then rise 2, run 1. And it's definitely a very straight figure. It's a line, so it has some symmetries, I suppose you could say, in that way, but not around the origin any longer. It's not going to be able to spin on the origin and meet up, so it lost its symmetry. Actually, the three that we talk about is x-axis, y-axis, and origin. So it's been shifted. We're going to learn about shifting in just a minute, but it's been shifted away from the origin, and we can no longer spin it around the origin to see its symmetry. Okay, but officially, the way we're supposed to check for symmetry, for what we think, if we think it's going to be symmetric with the origin, we have to change our y to negative y and our x to negative x, right? We change both of these for origin symmetry. So let's do that. Let's go down here at the bottom. Y equals 2x plus 1, right? It says g of x. That means the same thing as y equals. So if I change y to negative y, and I change the x to negative x, can I show that that's equivalent? Is there a reason it would be equivalent? And it is not, because we have a negative y, and then that would make that negative 2x. But this 1 on the end, that's really what messed us up here with our symmetry. It's not going to change its sign. So if I divide out the negative to change all the signs back, I'll have a positive 2x, and that will change that. So it will not be what it was originally. All right, so no symmetry. So it's not even nor odd. So that's a neither should be your answer. And then lastly, I suspect that this one might have a symmetry like the parabola. I see the x squared, and again, you might be using your calculator app and check it out that way. I don't know what that one looks like. So, but I'm going to do it algebraically. How do I prove whether it's symmetric with the y-axis? If x can be changed to negative x, and it doesn't matter. So this equation is y equals, or h of x, which is y equals x squared minus absolute value of x. So if I change my x to negative x, and this other x to negative x, is there a reason you can justify that it's equivalent? And sure, we can. We know that a negative squared is the same thing as positive, and we know that these absolute value signs make that, whether it's negative or positive, it would not matter. So, and also just kind of looking at it, that one's to an even power. We kind of learned that makes it an even function, and then this does basically the same thing. Whether x is positive or negative, the absolute value signs protect that. The sign doesn't matter. Now if I had a plus 1 on the end, or maybe a plus x cubed, maybe that's what I want to say. If I had another exponent, then that might throw it off. The constant actually wouldn't have hurt anything, but if I would have had an odd power out here, then I might have had some trouble. But so that one's actually is an even function, symmetric with the y-axis. All right, so some other examples. I think we talked about all these. X squared is, absolute value is, x to the 4th, that even power. And in general, if the x can be changed to negative x, that's the way it would look symbolically. For odd functions, that's symmetric with the origin or rotating it 180 degrees. Our example is our rational function, our cube function, our cube root function. And then we had one other, didn't we? Just our x, y equals x function. And in general, that officially looks like this. You can change the x to negative x and the y to negative y, and it comes out exactly the same. All right, so that's our little blurb about symmetry. And maybe it made it sound more complicated than it really is. Usually you can just graph it using your app on your calculator. You can graph that and just look at it and sometimes tell visually what the symmetry is. But if you have an exception where you need to prove it algebraically, I just needed to, as your algebra teacher, tell you that rule. Okay, now we're going to move on. The rest of the lesson is about now moving these basic functions, how to move the parent functions. So there are some various things that we can add on around our function, like you'll see this first part, our lesson. Hopefully you're following along with the handout that's in your module. So here's an absolute value parent function with a +1 to it. We're going to explore what that does. Here's a square root function of x with a -1 on the end. And then our x cubed, that's our parent function, with a +2. So what we're going to learn, the first one is a vertical translation. We know vertical means up and down, vertical distance. And for b values greater than 0, so assuming that b is a positive number, if we add a b to our parent function, the graph is shifted up that many places. And if it is a negative b, it's going to be shifted down. So the adding or subtracting on the end just shifts the graph up or down, a vertical shift. So this first one, absolute value of x +1, moves the graph up one place, like so. Square root -1, normally, you know, it's here at the origin, move it down 1, like so. And then here's our cube, and +2 moves it up 2, like so. So that's called a vertical shift. Just if there's an independent number added or subtracted, not included inside the absolute value sign, I'll call that the action or the operation sign. This, if it's in there, we're going down to this next one. But if it's an independent value outside of this action of the operation, independent, added or subtracted, that's called a vertical shift. It moves it up or down. Now the next one, the horizontal, is a little tricky because it does the opposite, and that's what all this kind of explains. You can read that. If it says x minus d, which makes you think it's going to be minus, but it actually moves it to the right, which normally we think of as being a positive move. And if it's a plus d, it moves it to the left. So it does the opposite direction. My colleague Rick Conley likes to say, I'm going to give him credit for that, he'll say the y never lies, so the y shift up and down, y never lies, but the x, the left-right shift, is a double crosser. So this guy's a double crosser. He does the opposite of what you think he's going to do. All right, so now look at our examples. Here we have all these parent functions. Here's our absolute value parent function, that's the v. Here we have, let's see, that's squared. Can you see that okay? That's our parabola parent function, and so on. So we have all these parent functions, and they've got, this is included in the action. That's a horizontal shift. So, and it's opposite, so that's horizontal right 1. All right, so we'll call this number 1. So this first one takes the v over one place to the right. Now, when you're in doubt, if you start doubting yourself and these rules, you forget, just plot a point or use your graphing calculator and verify it. But it's good to kind of be aware of these rules regardless of the method. It'll help kind of guide you. You'll be stronger if you do know that. The next one, number 2, the parent function is the x squared parabola, and it says +2 here, so we're going to go back 2. So there's our parabola, move back 2 places. Okay, number 3, square root function. Now notice they're trying to show us that this is, let me see, write this down, y equals the square root of x minus 2. The x minus 2 is in a parenthesis to show that it's under the radical with it, assumed to be. So that is a horizontal shift. If it was outside here, remember that's what we did up there, that's the vertical. So that means take your square root function, oh, moved it the wrong way, +2. It's always lie, that's the lie, right? The double crosser. The one that's horizontal is opposite. Okay, number 4. So we've got 2 things. Now we're adding in here. We've got to move it horizontally to the left 2 and then up 3. And the parent function is our absolute value, so that's the v, back 2, up 3, and that would be where the v starts. Okay, number 5. Number 5 actually has a couple of things going on here. One that I'm not ready to talk to you about, which is the negative, which we're going to talk about the very next thing. So I won't be able to complete that. But I can tell you that this +1 in the parabola will move it over back 1. You know, if it's included in the parentheses or included in the operation, you do the opposite. So back 1, and then this is really a positive 1. The negative sign's after it. The negative sign is a multiplier in front of this, and that's exactly what happens down here. So we're getting ready to talk about that. But as far as the shiftings, what I would call a shifting is back 1, up 1. And I know it's a parabola, but which way should the parabola go? Upright? Everything so far has been upright. I haven't mentioned any turning things upside down, and that's exactly what I'm teasing you about. The next thing is it's flipped upside down. This is this. The negative in front of this, and then that's a +1. The negative in front of our function is called a reflection. Whenever we have a negative in front of the entire function, like we see here, that's a reflection across the y-axis. So we flip it basically upside down. I would call that upside down in my words. But officially it's called reflecting across the y-axis. You know, if you look at, you know, now wait a minute. That is an oops. That should be across the x-axis. My bad. Please fix that on your handout. I'll need to make sure I go back in and fix that. I'll try to do that before I send it out. So if you get this video before I've got that fixed, I can't remember if I've already attached it. It should say X because it's upside down. So my bad about that. But we should have an upside down parabola, which would be like normally it's up here. That's the parent function. And if we flip it across the x-axis, like it's upside down this way, that's reflecting, like if you had a mirror here, reflecting across that x-axis. All right, so make sure you fixate. Make sure I fix that. That's what we've got here. The other thing, if the negative is only on the x intensely, just included on the x, that's across the y-axis. That's the left-right shift. All right, so what we've got here is definitely an upside down. And that's the ones you mainly see in your homework, by the way. The negative is in front of the entire function, flips it upside down. So we have a shift back 1, up 1, and then we should have an upside down parabola, something like that. Okay, the last type of translation is stretching and shrinking of your graph, and that happens when you have a multiplier in front of your function. So the a value times the function can be obtained from the graph f of x by stretching it vertically when a is greater than 1, and it shrinks it when a is a fraction between 0 and 1. So the graph, shrinking the graph vertically makes it look wider. Stretching the graph vertically makes it look skinny or more narrow. The graph is more narrow. Okay, so let's see some examples of that. Y equals 3x squared. The multiplier 3 in front of it is going to make it, which one? Skinnier or wider? If the value is greater than 1, it actually makes it look more narrow or skinny. If it's a fraction in front of it, it's going to make it look wider. This one flips it upside down, makes it look wider. So wider, shifting it 2 places. Up, that's a vertical shift. The negative flips this upside down. This moves it 2 to the right. The negative flips it upside down. Oh, 5 over 2, that's tricky. It's 5 over 2, even though it's a fraction, it is greater than 1, right? 5 over 2 would be 2.5, so that's actually more narrow. And then it's a square root function. This has got everything. It moves it to the right by 1 and vertically by 2. So a little bit of all of the rules there. We're going to practice this in a bit. And then this one has everything too. It's got the negative here, which flips it upside down. The 3, which is greater than 1, if it's greater than 1, it's more narrow or skinny. This moves it to the right by 2 and down by 2. And then we have a summary. There's 5 things there. And we'll come back in on the next video and talk more.